Okay, colleagues, let's start. Hopefully, if there's anybody watching on VR, the proper working stream is on YouTube, and the link to YouTube is in Microsoft Teams. Okay. So we discussed last time all of these deep epistemological problems, which, in a certain sense, these skeptical problems. I mean, from the very beginning, we can think, and actually, this is an important topic even for us today, especially in the sense of methodology, like properly speaking, methodology of science. So supposedly, there are two basic methods that human beings can use to establish the truth, and these two methods are empiricism and rationalism. Empiricism and rationalism. And empiricism is supposed to rely on experience. And rationalism is supposed to rely on pure reason or pure logic. Now, since ancient times, I think there was a certain parity, there was a certain uncertainty or question, which one is better, which one is more reliable, maybe. But I think that especially today in the 20th century, starting with Descartes, actually, to some extent, empiricism has been in ascendance. So if you can make a logical argument that says time is an illusion, or if you can make a logical argument which says 1 + 2 + 3 + 4 = infinity, right? We don't accept these kinds of arguments. Again, it's like, actually, this year, Roger Penrose got a Nobel Prize for, most importantly, for operationalizing the idea of black holes within Einstein's general relativity. And what Penrose has shown is that at the center of the black hole, there should be a point of infinite density. Or when we talk about, let's say, the Big Bang, again, we get to our mathematical models give us infinities, or sometimes we divide by 0. And you see, if we were rationalists, we would say, yeah, this is the logical derivation, we should run with it. But as empiricists, we have never seen infinities. We don't know what an infinity is. So let's imagine, let's say, an object whose black body radiation is infinite. What does it mean to have an object with infinite radiation? Or what does it mean to have a point in space with infinite energy or infinite density? We do not have a direct experience of anything like that. So it seems that empiricism, in an important sense, is above rationalism. So, like, at the end of the day, we know that mathematics works because it works in experience. Although the relationship between the two is kind of, it is problematic, because it would be stupid to say, let's say that you know that 2 + 2 = 4 because you've done experiments. Sort of that, Stanford scientists have conducted over 1 million experiments and they have actually found that 2 + 2 is not 4, but 2 + 2 is 4.000000001. So it sounds ridiculous, right? We think that logic is supposed to, have this innate reliability. But if we think about this carefully, there's a problem. The biggest so empiricism, by and large, relies on induction. And the biggest problem with induction is that if you think, again, last time we talked about Descartes and his experiment with Cartesian demon. So induction relies on sense data, on data of your experience. Well, it could always be that your sense data is misleading you. It could be that you are hallucinating, or maybe that you are making a mistake. So induction, in this sense, is deeply problematic. Not to mention that, again, induction, strictly speaking, only talks about the past. So you can say, in the past, this hypothesis worked. But what's going to continue into the future? How will the world continue to behave in the future? No one knows. It's like, let's say Galileo's law, F = 1/2 gt². Okay, so strictly speaking, this law is not obeyed 100% because of quantum mechanics and Einstein's general relativity. But let's imagine. So in the past, you see this law working, but how do you know that it will continue to work? Again, Newton with his famous equation. So F equals m1 multiplied by m2 divided by r² multiplied by the constant g. Newton very famously said, he used this Latin phrase, something like hypothesis non fingo, translated into English usually as I do not feign hypotheses. I do not invent hypotheses. And when Newton said that, he meant that he doesn't know why this equation holds. He says, I can look at the sky and I can observe that this equation holds. But what is the deep fundamental reason for why this equation holds? Newton says, I do not know. Could it be that in the next moment, all of known physics will break down? Maybe. There's nothing in our equations to tell otherwise. In fact, remember, I read you this quote by Jean-Paul Sartre. Sartre seems to have this idea that nature is radically contingent and that anything can happen in the next moment. But we don't have to be this extravagant. We can say, no, it's not anything can happen in the next moment, but only certain things. Certain things can happen. Like they have to follow at least some logic. And that's okay, because I can give you a million different rational scenarios which are not ruled out by contemporary science. And these scenarios would result in basically all of us being like turned into a pile of goo in the next moment. We will evaporate. So, for example, there's a calculable probability that we will be hit by a gamma ray burst, and all of us in this room will die in the next second. In the next second. In the next second. There's a calculable probability. It could happen, right? So, a disconcerting thought. It's not pleasant to think about it, but it's a possibility. Or so this does not involve changing the fundamental laws of physics, but I can imagine a scenario, or like science can imagine a plausible scenario how the laws of physics could change in the next moment. So the Higgs field is very important. The Higgs field gives mass to not all but many of the subatomic particles, and there's a possibility, there's a hypothesis that maybe Higgs field is in the state of a false vacuum. And it could sort of quantum tunnel into a different state. So it's like I think that the picture that the physicists give us is something like this. That sort of, yeah. So if this is, let's say this is, no, this is not time. I'm not sure exactly what this is, but this would be the value of the Higgs field. And the Higgs field currently sits at this value. But if somehow through some random fluctuation it would get over this bump, then it would suddenly and momentarily change at the speed of light throughout the universe to this new value, and this would break all of known physics. And incidentally, well, it depends on what these values are, but it could be that sort of stable atoms would become impossible in the next moment. Stable atoms would become impossible, right? So this is an interesting, disconcerting idea that sort of, again, phrase of unknown unknowns. So in a nutshell, this is the problem of induction. On the rationalist side, you also have a problem, and this is the problem of deduction. The problem of deduction. So problem of induction. Here we have the problem of deduction. Now, some of you may want to do a presentation on this because it's an interesting, although slightly technical topic. But basically, the idea of problem of deduction is that if you want to demonstrate the reliability of logic, right? If you're trying to prove logic, you have to first assume logic. So in order to substantiate logic, you need to assume itself. Assume the logic, the validity of logic itself. Once you have assumed that logical thinking is valid, you can then use it to prove that logic works. But how can you assume that? This is a definition of the vicious circle. Among other things, I think in my head, the problem of deduction should be associated with the name of Ludwig Wittgenstein, although I'm not exactly sure. And Wittgenstein would point to the fact that sort of sometimes you just follow rules without, like you follow a rule not according to a rule, but you simply have a background ability to follow the rule. But it's like, if you have to follow a rule according to another rule, then you follow the rule according to the rule, according to the rule, according to the rule. It's like you have this infinite regress. This is, I'm not going to try to explain this because it's slightly technical and slightly boring, but the most famous article about this was actually written by Lewis Carroll. Lewis Carroll, a famous British writer, I would like known to you as the author of the Alice in Wonderland. He actually wrote a very important paper in the philosophy of logic. And the name of the paper is What Tortoise Said to Achilles. Что черепаха сказала Ахиллесу. If you want to look it up, it kind of, I mean, it's a complicated argument, but the upshot is this. You have to assume logic in order to prove the validity of logic. Not to mention that you can get into all sorts of complications, like, for example, Gödel's incompleteness theorem, that actually, even if you could assume that logic works, most of the logical systems you would not be able to prove. So Gödel's incompleteness theorem is a strict formal proof, is a mathematical proof. Okay, excellent. Is a strict mathematical proof of the following proposition, that no logical system rich enough to encompass arithmetic. So if you take a logical system which is strong enough, which is robust enough to be the basis for mathematics, arithmetic, no system like that can prove itself. That in a system like that, you have to have statements which cannot be proven but have to be assumed, right? And that's a problem, because, you know, if you cannot prove, you have to assume. Yeah, well, how do you know that your assumption is correct? How do you know that your assumption holds, right? Anyway, so these are sort of basic preliminary sketches. Let me pause now and let me just go off into the left field. Let me talk about, sort of restart this discussion in a historical fashion. So we have talked about Descartes and his fear of this possibility of the Cartesian demon, right? This evil demon deceiving him. And we talked about David Hume's criticism of induction. And people were impressed at the time. And you have to remember that in Descartes' time, science was not yet very well developed. But over the years, science has progressed, and science has achieved certain things which were deemed, you know, fantastical and impossible. And so over the years, I mean, in Descartes' time, it was much more easy to be a skeptic. And you have to understand that a lot of people in Descartes' time full well expected, you know, second coming of Jesus any moment, and sort of the whole world to be consumed by fire. Our knowledge of the universe was much less robust in Descartes' time, and it was much easier to doubt the conclusions of science. But once science has gotten going, people became incredibly confident. And the most important result was Newtonian discoveries. And I mean this very seriously. People almost worship Newton as a god. Well, I mean, I'm exaggerating a little bit, but Newtonian results of Newtonian physics were perceived as completely like outstanding, sort of groundbreaking. Why? Because you had a simple formula which explains such enormous complexity. And it's hard for us to understand right now. But again, for the ancients, there was this huge and hugely important barrier between the world up there in the sky, so stars made of some kind of fifth element, which is inscrutable to science, and the Earth down here below, right? But the problem is that this formula, Newton's formula, it explains both. This is a unification. You unify, sort of using this formula, you can calculate the trajectory of a cannonball that you shoot out of a cannon, and also the trajectory of the moon, and also the trajectory of galaxies. I mean, we know that the predictions are false because of Einstein's relativity, but back in the day, people did not know this. And this looked completely miraculous. And this was much more robust and much more elegant than anything that came before Newton. I mean, like Copernicus, Ptolemy, Kepler, Galileo, you know, forget about all of them. Newton was like mind-blowing, right? So basically what I'm driving at is that I think that the degree of skepticism among intellectuals really decreased quite substantially, quite dramatically since the time of Newton, and many people were very optimistic. So optimistic that actually Lord Kelvin, the person after whom the Kelvin scale is named, said around the year 1900, I think, don't quote me on that, he said, physics is almost done. Physics is almost complete. We have almost discovered everything that there is to be discovered. And they have baptized the smallest units of matter, atoms. They said hydrogen is an atom. Atom in Greek means atom, something that cannot be cut. So the most fundamental substance below which you cannot go. This is how ambitious people were. Right? Today we know that atoms can be cut. So technically speaking, it's a misnomer. The physicists jumped the gun. They used the wrong expression. Atoms very much can be cut. But at the time, people were very confident. And so what happened is basically, well, there were two catastrophes, and Einstein was involved in both. Einstein actually got his Nobel Prize for his work in photoelectric effects. So this is not exactly quantum mechanics, but issues which are going to lead to quantum mechanics. So the science of the very small. So on very small scales, Newton was beginning to break down. And on very large scales, so when we look at astronomy, Newton was also beginning to break down. And so people were very disconcerted about this. And the name, another word, Chandrasekhar's advisor, Eddington. Eddington was able to observe the bending of warping of space-time predicted by Einstein during an eclipse in Argentina. And this was, as far as I can tell, this was the final nail in the coffin. And a lot of people were very upset because for ages, we have believed Newton to be completely correct, like proven to be true. And suddenly we see that he is false. This is exactly David Hume's nightmare, the nightmare that David Hume gave us. We think that something is true, it's supported by evidence until it is not, right? So let me try to be more specific now and slightly maybe, prove my academic credentials a little bit. This is going to be the only class in proper philosophy of science that you get, throughout the whole academic year. So if before I became lecturer at ISAF, the things I'm going to talk about in the next 15 minutes is the only thing you studied, the only thing you covered in this course. So we begin, and this was the first class of the first course. We begin in Vienna in the beginning of the century. So a bunch of people, scientists, many of them physicists, some of them chemists, and they were very impressed by Einstein. And they thought everything can be salvaged. We just need a better theory of philosophy. We just need better philosophy. Old philosophy was wrong, but we'll find a better philosophy which suits contemporary science and which will be able to tell us what we can assert and what we cannot assert. So the leader, and they were called the Vienna Circle, Vienский кружок. Among the leaders were people such as Moritz Schlick, Rudolf Carnap, Alfred Ayer from Britain. So let me, I think Schlick was Schlick was the most senior member. So maybe I should write his name. He tragically died. He was killed by a fascist terrorist. Tragic story. So their whole approach will later be called verificationism. Let me just write verification. Verification. So verification associated with the name of the school, Vienna Circle. So Vienna. And again, well, let me write two names, Schlick and Carnap. Carnap will later go to the United States, and he will become instrumental in developing later philosophy of science. So basically, all of contemporary philosophy of science, I don't want to say all, the vast majority of everything that falls under the rubric of philosophy of science goes back to the Vienna Circle, even the people who will disagree with them. Carnap was a scientific advisor of Thomas Kuhn. I'll talk about him in a second. And so the idea of verification, well, they had I suppose two ideas. First is we want to very cleanly separate theory statements from observation statements. They wanted this very clean separation, saying, look, this is my scientific theory, this is the logical part, this is the observational part. This is what I observe, this is what I logically deduce. This was the first bit. And the second bit, much more important bit, is that the verificationists said that in a proper scientific theory, the evidence confirms the theory. In a proper way of doing science, the evidence confirms theory. So I'm going to draw something like it's not going to be very rigorous, but you have to use your imagination, right? So let's imagine. Well, again, let's talk about astronomy because that's always the easiest. I mean, in principle, it would be nice to talk about economics, but economics is just so much harder to to give vivid examples, easy to understand examples. So let's use astronomy. Astronomy genuinely is a much simpler science. I mean, we can predict solar eclipses much better than we can predict economic crises. And I gave you the reason. The reason is that complexity, the degree of complexity, these self-interactions, chaos theory, say mathematical way to formalize it. Okay, so let's imagine that this is time, and this is by x. Let's say I abbreviate x, y, z, right? So a planet or a star has a position in position in this four-dimensional space, time and XYZ coordinates, three-dimensional coordinates. So it's three dimensions of space and one dimension of time. But I'm going to abbreviate the 3 dimensions of space just using this one, right? And so let's imagine my observation looks something like this. And so what the Vienna Circle wanted to say is that, look, wonderful, you see this, just take the dots and use statistics to fit a line. Find the line that fits best. Let's imagine this is your line. And so you go from the blue observations, you go through from observations to theoretical conclusions. And they say that theories that are confirmed by data, true. Theories which are disconfirmed by data, false. And it was also very important for them. They wanted to fight against metaphysics and against theology. And said metaphysics and theology just doesn't work this way. I mean, existence of God has no relation to this picture. So therefore, they said statements of religion, metaphysics are, strictly speaking, nonsensical. They do not mean anything. So when I say, I believe in God, or I believe in that Jesus is the Christ, I might as well be doing this. I'm making noises through my face, but they do not mean anything. Maybe they have a social meaning in the sense that I'm saying, like, go America, or go Russia, some of this. So in this sense, religious statements could have a meaning, but they do not have any kind of scientific meaning. They cannot be true or false in this sense. They are meaningless. This was important to the Vienna Circle. And this idea that your statements have to cash out in empirical evidence is an idea that we by and large retain to this day. So even people who are going to criticize the Vienna Circle, by and large, would be, it's not as extreme. It's not as extreme. But if you propose a theory, you'd better be able to explain how it relates to the data. You ideally propose an experiment. If you cannot propose an experiment, at least tell us what kind of an experiment could in principle be proposed, right? So when we talk about multiverse, for example, people talk about how you can see traces of different universes within our universe, be it cosmological multiverse, let's say created by cosmic inflation, or be it quantum mechanical multiverse of the many worlds interpretation of quantum mechanics. The idea is that we're trying somehow to for our theories to cash out in experience, which is why, again, I think in a certain important sense, empiricism über alles. This empiricism is the alpha and omega, I think, of our contemporary philosophy of science. We take this very seriously. It's not enough. Empiricism is not enough, but it is the necessary basis. So all of this, very briefly, very quickly, fell apart. And the immediate reason is that, look, when I talk about these points in a line, what do you mean best fit? How about I draw this line? Or maybe I can draw some kind of line like this. They all fit very nicely. Now, what kind of mathematical measure do you want to propose to say that, let's say, green line is better than red line or is better than blue line? So, and mathematicians in the room, you understand that if I give you a finite set of points, there is an infinite number of lines that you can draw through them, infinite number of functions. In fact, I think an infinite number of even analytically continuous functions, right? So there's this wonderful thing called Fourier transform, transformatio Fourier, which allows you to turn any, like decompose any line whatsoever that you want, not line, but set of points whatsoever that you would like to draw, decompose them into a series of sine waves. Разложение на синусоиды. You probably know this better than I do. Okay, my mathematics is getting rusty these days. So this was the big problem. So the idea is that it doesn't matter how many instances you observe. You can never say that your theory is verified. This was sort of the biggest problem. And the examples were there. They were very obvious. I mean, if you think of Ptolemaic astronomy, geocentric Ptolemaic astronomy, Ptolemy, the ancient astronomy, that thought that the sun is at the center of the universe, that Earth is at the center of the universe. And broadly speaking, they had these ideas. Oh, this is not going to work. Epicycles. So the Earth is in the center, and then around the Earth you draw a circle. Now, if you look at the sky, obviously nothing moves in perfect circles. Even the moon doesn't go in perfect circles. But if you imagine that on this circle there's a point, and on this point there's another point, on this point there's another point, so you have a system of circles, which is more or less exactly what Fourier transform does. Ptolemy, and this was a hugely brilliant mathematical achievement of ancient, both ancient astronomy, observations, and also of ancient mathematics. He was able to explain the motions of everything he could see in the sky using this kind of system. This is called Epicycles and difference, Epicycle in Russian. And so his theory was confirmed. It fit the line perfectly. And if it did not fit perfectly, you just have to add a couple more circles. You add a couple more circles and everything works. And it doesn't matter what your motion looks like. Your motion could look like this or something. Just pile on circles. It's a wonderful, illustration. If you type into Google Homer Epicycles, you will see how you can use Epicycles to draw a picture of Homer Simpson from The Simpsons, right? A trajectory using these perfect circles that will actually approximate his picture. So anything can be done in this fashion. And so verificationism, in this sense, unfortunately, has failed. And everybody knows it has failed. Even the founders themselves understand that it has failed. But it produced something in its place. So the second theory was developed by also an Austrian philosopher whose name is Karl Popper. Some of you have met him last year. I would not necessarily recommend his political philosophy, let's put it mildly, but his philosophy of science is very good and still very influential. So here we have verification, here we have falsification. Falsification. I think his most important book is called Conjectures and Refutations. So like hypotheses and falsification of hypotheses. Also, he was not a member of the Vienna Circle, but he was a friend of the Vienna Circle, and he came from time to time just to. Wow, people are writing in the chat. Anyway, no way I'll be able to read what the chat says. So falsification, associated with the name of, again, Karl Popper. And what Popper said is that, look, there is this interesting asymmetry. There's this interesting asymmetry. If you're trying to verify, even an infinite number of observations is insufficient. But if you're trying to falsify, let's imagine I give you another point. I give you another point, and this point is, I don't know, somewhere over here. You say, whoops, I know that the green line, the blue line, and the red line do not pass through this point, so I can rule them out. Notice, so again, so how many observations do you need to confirm? Infinity. How many do you need to disconfirm? One. Example, the textbook example. I say, all swans are white. You give me one black swan, and my statement is wrong. If I try to prove the statement, all swans are white, well, in the way that it's logically phrased, I need to observe an infinite number of swans in all the branches of the multiverse in all the world. Only then am I justified in saying that all swans are white, right? Essentially. I mean, swans, that's not a very interesting example, but let's imagine, let's say the charge of the electron. We want to say, no, the charge of the electron is changeless, and it's this anywhere and everywhere, right? And it's kind of truly a constant. It's a problematic assertion to make, right? So Popper has this notion that science progresses not by bringing us closer to the truth, but by bringing us further away from falsehood. Not by bringing us closer to the truth, but by taking us further away from falsehood. The trouble is that, of course, there's an infinite number of false statements. So in principle, you could be still staying in one place. But, you know, that's neither here nor there. And this is a very hard idea to this day. And like scientists, I think, read literature in philosophy of science with a lag of about 50 years. So this is still the hottest idea in philosophy of science today. Very often people will talk about this. And I think it should be taken very seriously. Again, if you propose a theory which cannot be falsified in any shape, matter, or form, no evidence can falsify it, chances are your theory is not very interesting. Or maybe it's nonsensical, or maybe it's stupid, or maybe it's pathological. Maybe there's something pathologically wrong with your theory. Maybe it's a lie or some kind of a swindling schema, right? And I think that this part of Popper probably stands. Yeah, like if you make an assertion which makes absolutely no difference to the empirical world, as Wittgenstein says, an element of the system which does not move with the rest of the system cannot be considered its member. Like, okay, it's a complicated way of phrasing, but yeah, it's like really, really nonsensical. So And I think that this is something that even today we retain from Popper. But the problem is, alas, this does not work either. And you can think of some ideas, you can think of some examples why this does not work, but the most obvious way to state this is that, look, if you get an observation like this, the immediate thing that you could say is very simple. This is a mistake. Your telescope just glitched out. And okay, but I say, no, my telescope is right. Let me try to prove it. It's sort of, how much do I need to prove that? Like, if you really, really, really want to hold on to the assertion that your instruments are wrong, your thermometer is off, your clock is off, your telescope is off, there's no way you can argue against that. Sort of, could it be? I mean, for example, one important issue in contemporary cosmology is that the universe is expanding. Hypothetically, due to dark energy, although nobody knows what the heck dark energy is, but this is one of the assertions. If you could say, no, there's actually something wrong with our telescopes, and they give this systematic error, but actually the universe is not expanding, it's not clear how exactly you would go about disputing that. So it's always possible to hold on. Like, it's always possible to hold on to any theory. Like, if you're willing to be clever enough, you can even, defend the view that Earth is flat. And you just need to introduce enough enough things which are this did not go well. Sorry, which are called auxiliary hypotheses. So the third approach I will call sociological, broadly speaking. And the sociological approach, probably most importantly, is associated with the name of Thomas Kuhn. And again, as I told you, Kuhn was friends with Popper, and he was a student of Karl. So all of these people are actually in the same camp. But in addition to Kuhn, another important name in the field is Willard van Orman Quine. If you go talk to Krista will tell you endless stories about Quine, because he's it's not like he's met. He was constantly bumping into Quine in Yale, I think, and Krista can tell you how he was when he worked in the library, and Quine came daily, and they had little chats. But Quine is a very important philosopher. Quine is one of the most important names in Anglo-American analytical philosophy of the second half of the 20th century. He's one of the biggest names, period. And in fact, when I used to teach this course as a regular philosophy of science course, Quine was the culmination of the whole course. Like, if you want to know what is, properly speaking, the right philosophy of science, it's Willard van Orman Quine. So actually, these two approaches I have trashed. This one I'm going to defend, but it is a very disconcerting, very pessimistic approach, because this approach throws hands up in the air and says, unfortunately, the choice between theories is not rational, but irrational. We choose what to believe, not based on rational reasons, but based on irrational reasons. Because it's simpler, because it's easier, but also for political reasons, such as who gets the funding, who gets the grants, who gets appointed to positions. But at the end of the day, sort of this is the real foundation of science. Sort of sociological consensus and not truth is the name of our game. Okay, let me explain it. So, and the word I need to throw on the board is auxiliary hypotheses. Auxiliary hypotheses. So an example of an auxiliary hypothesis would be, my telescope is working correctly. That's an auxiliary hypothesis. Alternative would be, my telescope is broken. And the problem is that when you do science, so imagine I come into a laboratory and I'm trying to perform an experiment. How many auxiliary hypotheses do I need to have? Do I need to explicitly have? The problem is, sort of, you say, okay, I assume that my microscope is working correctly, that my glasses are not distorting the view. I assume that there's no hallucinogenic poison in the air. I assume that there's not a telepathical pink unicorn who messes with my brain. I assume that there's no Cartesian evil. And the problem is, you have to assume an infinite number of things, especially once you start entertaining these weird possibilities. And so let me try to, again, bring this to home, closer to home, by giving you a concrete example. So Newton, right? Newton overthrows Ptolemy, right? The Newtonian system substantiates the Copernican worldview, and so with the help of Newton, the heliocentric system overthrows the geocentric system. Again, I use these examples because they're the simplest one to use. And the sociological approach is going to say things were not so simple, especially before Newton came. People who, even Galileo, who thought that the Earth was stationary and moved around the sun, his ideas were he had a lot of mistakes. So he had what we think is the right conclusion, not exactly right conclusion, but approximately right conclusion, but for somewhat wrong reasons. And it's kind of interesting when Cardinal Bellarmine, because you all know about the persecution of Galileo by the Catholic Church, when Cardinal Bellarmine came to talk to Galileo, Galileo actually has shown his conclusions through the telescope. He invited Cardinal Bellarmine to look through the telescope and see with his own eyes what goes on. And when Cardinal looked at that, telescopes were very new at this time. Cardinal said, "What the hell are you showing me? I see just some smudges. How the hell am I supposed to know that what you're showing me is really real and not just some figment of imagination?" So one possibility, among others, was that maybe my battery is running low, unfortunately. One possibility maybe was that it's not that what telescope is showing to Galileo is just meteorological phenomena. So what Galileo observes, for example, he observes the moons of Jupiter. How do we know that these are really moons of Jupiter and not just some things in the atmosphere, like in the clouds? So it was very hard to do back to verify or falsify back in the day. Okay, so I guess I'm going to have to, because otherwise the stream will cut off, which is not a very good idea. I should have charged that before, I hope. Anyway, so the story that I'm going to tell you is the story of now not of Ptolemaic astronomy, but I'm going to tell you the story of Newtonian astronomy, the wonderful and wonderfully successful Newtonian astronomy and things that were potentially wrong with it. Now, the most important idea sorry. I hope I'm going to be able to sort this out in a second. Oops. Yeah, so now, wow, everything falls apart on me. As I said, I have to keep repeating, technology hates me. Anyway, so yeah. So Newton, right? Newton explains the trajectories that we see in the sky. Obviously, by the way, another thing to remember is that you never see observations precisely. There's always error bars. There's always imprecision in your measurement. So you can never precisely pinpoint the location. So this always introduces complexity. So Newtonian system worked very well while the telescopes were not very powerful, right? And so basically, let me give you two issues. So the first one has to do with the orbit of Uranus. And the second one has to do with the orbit of Mercury. So first, people looked. I'm not even sure if I'm going to draw anything. Well, anyway, yeah. So people looked at the trajectory of Uranus, and it was different. It was different from what Newton has predicted. And people said, well, you know what? Maybe there's another planet that skews the orbit of Uranus. They tried to calculate where this planet theoretically would be. They searched for it, and you know how the story ends. Lo and behold, they have found Neptune. And once they have found Neptune, everything falls back into place. Now, okay, everything is fine again. The orbit of Uranus corresponds to observations. Mercury, same exact problem. If you want a kind of interesting pickup line, so next time you want to impress somebody, tell them about this Mercury business. So this is called the precession of the perihelion of Mercury. Mercury, let me repeat that. It's a wonderful phrase. Precession of the perihelion of Mercury. Precession of the perihelion of Mercury. I can even say it in Russian. Прецессия перигелиона Меркурия. Right? So, let's not go into details. But it's actually not difficult to explain. Perihelion is the point of closest approach. So perihelion of Mercury is the point where Mercury is closest to the sun. This is what perihelion means. And precession means that it moves around. So there was a movement around, deviation of the closest point of approach. And people, the first thing, and again, notice, what should the verificationists say? Whoa, throw the theory out the window. What does the falsification say? Popper says, throw theory out the window. What did people actually do? No, people are irrational. Look, we've already printed the textbooks. We've already given doctoral dissertations. We cannot just say that Newton was wrong. Let's try harder. And so people have postulated the planet by the name Vulcan, which was supposed to be even closer to the sun. And the idea was that because it's so close to the sun, and our telescopes, you burn your eyes if you look that close. We just cannot see it, but it's there. And they have calculated Vulcan, and in fact, many people claim that they have discovered Vulcan. But there's always also some problems. But then comes around Einstein, and he says, no, this is not a solution. The solution is that actually the whole theory is wrong. This theory is wrong, has to go out the window. And we replace this formula with a different formula. And this different formula, again, Einsteinian general relativity, talks about how massive objects, the sun is a hugely massive object, warp space-time. And because they warp space-time, they introduce additional deviations, perturbations from standard theory. And Einstein gave his equation. It was simple, mathematically elegant, and it predicted the trajectory of Mercury brilliantly, to the degree of precision that we can, to this day, perfectly falls in line. Like every kind of test we have thrown at Einstein's theory of general relativity, it has passed. Now, does it mean it's true? Well, I'm kind of rushing ahead, but I cannot resist. Probably not, because it doesn't work very well with quantum mechanics. It's the same thing. So it's the same thing with Newton. Within the standard predictable regime, Newtonian mechanics worked very well. But once you push it to the boundaries, you see deviations. Likewise, with everything that we can observe within the standard regime, general relativity works very well. But inside of the black holes, or in the early universe right after the Big Bang, or like when we have something very massive and very small at the same time, we expect Einstein to break down. And one simple indication of this is because in Einsteinian equations, you have to divide things by zero. And mathematicians don't like dividing things by zero. It's a good indication that your theory is probably ultimately wrong if you have to divide by zero at some point. So it was not Vulcan. It was the idea that we have to throw the equation out. So now, instead of this equation, we have some other equation, which I'm just going to abbreviate Einsteinian equation. And we have today exactly the same problem. Exactly the same problem. We look in the sky, and the trajectories do not fall in line with the observations. In fact, I'm not going to phrase this very precisely mathematically, but I'll try to say it somehow, right? So when you look in the sky, how much can we explain? Like if you think in terms of like statistical variation, like what percentage of the movements of the bodies in the sky can we explain, and what percentage is just sort of disagrees with our theory? How accurate is our theory? I would ask if anybody cares to guess. People can write in the chat. Well, most people in the chat, I'm sure, or some people in the chat probably know the right answer. So the right answer is that our modern Einsteinian theory, well, actually, it's not called Einsteinian theory. It's called, well, no, I'm not sure what it's called. It gives you 5% accuracy. 5% accuracy. 95% of what we see in the sky, we cannot explain. It violates Einsteinian general relativity. So, and there are two problems. One problem is that there's too much local gravity. So local gravity appears too strong. So Einstein predicts that local gravity should be weaker, but it appears stronger. And so when I say local, I mean within galaxies. But if you look between galaxies, so globally, intergalactically, but intergalactically, gravity is too weak. So it's both too weak and too strong at the same time. So this is exactly this picture. And the question is, do we have a Neptune that we have to search for, or do we have a Vulcan and we have to throw Einstein out? Is it a Neptune or a Vulcan? So the Neptune, you know what Neptune is called, right? You name the planet before you discover it. This is called dark matter. And it accounts, I think, for roughly 20%. So we postulate, we say, there's 20% more invisible stuff in the universe. We cannot see it through telescopes. Nobody has been able to. I mean, physicists have candidates for dark matter, but none of these candidates have like any real proof behind them. We have never been able, like this imagination. We can imagine what these things could be like, but we have not discovered them, right? And this thing we call dark energy. Dark energy. And it accounts for approximately 75%, I think. Yeah. So if you're wondering why does matter and energy come into the same percentage, well, you can convert matter into energy. This is called E equals mc squared. So this is how you can compare matter and energy through this formula. And if you plug the relative numbers, you get 20% here, 75% here. This may confuse people, so let me erase it. But matter and energy are essentially the same kind of stuff. Like the universal currency of physics is energy. So energy content of the universe is 5% what we see, 20% this extra matter, and 75% extra energy. I should say that actually we see 1% of the 5%. We see 1% of the 5%, but from this 1%, we extrapolate that there should be around 5%. So these 4% are invisible, but it's plausible that it's there. But sort of, so from 1 to 5, you can get, well, basically you say, oh, there's all sorts of, dust between galaxies, so you can estimate how much you need. But you like even the highest, most optimistic estimates cannot get you beyond 5%. But what we really observe is only 1%. And so the options are simple today. So this option is dark matter and dark energy. And this is actually called, it has a name. This is called the lambda CDM model. I can explain what this means if you want to ask me, during the seminar. Lambda stands for the cosmological constant, and CDM is called dark matter. Lambda is dark energy, and CDM is dark matter. So this is the concordance cosmology. This is what most physicists believe today. But we do not know. Maybe it's wrong. The alternative, well, as you can imagine, there are many alternatives. But one that gets most traction these days is called MOND, modified Newtonian dynamics, and it says, no, stop looking for Vulcans. You're not going to find Vulcans. We need to change the equation. And you see, it's an interesting thing. Of course, you can find an equation. They have an equation which predicts everything perfectly. Problem is that this equation is not elegant, and it has a lot of free parameters. There's a lot of things you have to insert by hand. So scientists don't really like that very much. But you see, this is where irrationality comes in. Somehow, postulating invisible stuff is okay, but postulating invisible, free parameters is not okay. How do you choose between the two? So again, this is called irrationality of theory choice. Irrationality of theory choice. Now, I actually want to go off on a tangent and talk about dark matter, dark energy some more. But before I do, please tell me, how much time do we have left? Exactly. 10 minutes. Yeah, okay. I can talk about this for 10 minutes. So just to flesh this out some more, this is maybe slightly more technical, but still I like going into these things. So when we talk about dark matter, there are basically two main candidates for dark matter. And again, I'm explaining this. It has less to do with philosophy of science, but I want you to see the logic behind it. So one candidate for dark matter is called this is half jokingly, physicist sense of humor. Wimps, and the other ones are called machos. These are the two candidates. So WIMPs stands for weakly interacting massive particles. So we imagine that maybe there's an additional fundamental particle, like axion, for example, or maybe sterile neutrinos. The big problem with WIMPs is that we hoped to find WIMPs in the Large Hadron Collider. And Large Hadron Collider has not been able to come up with anything. And you see, this is the issue. Again, verification, falsification. You turn on the Large Hadron Collider, which costs, by the way, $10 billion. Let me put things into perspective. And you're not able to find them. One thing you can say, okay, our theory is bad. Another thing you can say, well, you just need higher energies. The Large Hadron Collider is not strong enough. It's like, you know, this Russell's teapot, that there's a teapot flying around Saturn. You say, you look through the telescope and say, I cannot see it. Russell says, you need a bigger telescope. Just prove that. That's almost exactly what the proponents of WIMP theory say. Say, we need a more energetic Hadron Collider. Guess what? You get a more energetic Hadron Collider, you don't find WIMPs. They will say, oh, we need an even more energetic Hadron Collider. And the problem is that, you know, each new collider will cost even more money. This one costs 10 billion. The next one, I think there's a proposal, and I think the tentative name is going to be Very Large Hadron Collider. I'm not making this up. It's kind of interesting what happens in the Hadron Collider. It's, again, I understand this is a digression, but I hope it's a fun digression. Again, you know, think back to Heraclitus, right? This idea that everything is in flux. And in general, the physiology, you know, Thales and Anaximander and Anaximenes, that everything can be turned into everything else. Anything can be turned into anything else. That's exactly what we do in the Hadron Collider. So hadrons is a special type of particle. The particular hadron that they are using in the Large Hadron Collider is actually simply the nucleus of hydrogen. So it's a very simple process. You take a box of hydrogen gas, and you shoot it with radiation. And radiation knocks electrons off. And then you use a magnetic line to separate the protons. So you take the nucleus of hydrogen atom, which is basically just one proton, and you then accelerate it using very powerful magnets running on you know, these liquid-cooled superconductors, close to absolute zero. And then what you do, you take two protons and you just smash them together. You run the beams into each other. And by smashing the two beams together, you can produce anything, any particle. And, well, can you produce a chair or a table or a person? Theoretically, yes. It would take a very long time. It's not a very efficient way to produce tables or chairs or people. You'd have to wait for, I don't know, not astronomical, but, you know, it's like incalculable number of years, maybe like 10 to the 10 to the 10 number of years. I don't know. Mathematicians can do the back of the envelope calculation. There's a very interesting Taj Mahal theorem, which kind of, a slightly different idea, but if you want, Google that. And Taj Mahal theorem actually says that you can, well, it's slightly more interesting. I don't want to go off onto a tangent. I'm just going to abbreviate it by saying that you can make anything out of anything. It talks about, you know, entanglement between quantum states, but, you know, let's not go there. So these are the WIMPs. And again, and the problem is we have kept smashing the protons and we have not seen the WIMPs. What are machos? Machos are massive, compact halo objects. So we would imagine that these are things such as maybe dust, rocks, asteroids, loose planets, very dim stars. So things like the kinds of things that we can understand what they're made of, but we simply cannot see. And you see, the problem with both WIMPs and machos is the same. For the WIMPs, our Hadron Collider is not strong enough. For the machos, our telescopes are not strong enough. So both can be neither confirmed nor disconfirmed. But in the meantime, you have to pay physicists' salaries. You have to print textbooks. You have to appoint doctors. You have to give Nobel Prizes. And the choice, whom do you fund? Do you give money to the Lambda CDM people? Do you give money to Mont people? Whom do you hire? And whom do you fire, therefore? Whom do you deny tenure? Who gets to be a professor? These guys or these guys? It's a problematic story. And again, people like Kuhn and Quine are going to tell us, you know, you got to understand that much of the reason, at least, and this is, I would say, more or less undeniable. I'm not entirely, but to a large extent, the only reason why we hold on to this and haven't switched on to that is because, you know, again, for reasons of sociological inertia. And this is what Kuhn calls the paradigm shifts. He says people are never convinced. Most people are never convinced. You just need to wait for the time to pass. The new generation comes and they change their opinions. But people, old scientists, set in their own ways. They will never make the change. Although at the end of the day, again, if you're willing to be clever about it, you can still hold Ptolemaic astronomy or believe that the Earth is flat. You just need to pile on more auxiliary hypotheses, postulate more and more Vulcans, right? So I mean, like, let's say the Earth is flat. but there's some interesting field that sort of screws with your optic nerves when astronauts go into space. So Earth is actually flat, but the kinds of things that they see in space, it's just, volcans, something, cosmic radiation screwing with their brains. So I'm joking, obviously, but that's the problem. That's the problem, that we look at science and it seems to be so spectacularly successful, but in its foundation, there's nothing there. It's completely foundationless. So people like Popper, and I think it's also Neurath had this metaphor, but maybe Popper says doing science is like rebuilding ship at sea, rebuilding the ship at sea. We do not have any kind of firm ground beneath our feet. And Popper says that we are trying to pile down foundations, but these foundations just sink into quicksand. There's nothing beneath our feet. And this is, I think on the one hand, quite exhilarating and very democratic, because you don't know, but Hawking also doesn't know, and Einstein didn't know, right? This is kind of democratic. Well, I mean, we shouldn't get too cocky about this, I think, but it's a fun thought. Although again, I think there's an important element of truth about this. Again, going back to Socrates. He is wise, who, like Socrates, knows that he knows nothing. But at best, we have these shaky hypotheses. So I actually mean this very seriously. Something else I wanted to mention in this respect, well, again, I suppose maybe the irrationality and this sociological element. And that's the story. So we go from verification to falsification. We end up with a sociological approach. Yeah, what do we do about it? Well, I mean, if we were robots, if we were trained to never accept logically subpar arguments, we'd just be stuck. We'd just be frozen and paralyzed by fear. But thankfully, or fortunately or unfortunately, human beings are irrational. Again, this is exactly what David Hume says. David Hume says, philosophically, I cannot dispel the doubts of skepticism, but I don't have to, because I wake up in the morning and I forget all about that. I think about my friends. I want to play a game of chess. As Hume says, reason is too strong for principle. Sorry, nature is too strong for principle, meaning that human passions are stronger than human reason. So we are willing to accept subpar evidence and jump to conclusions, right? And so does Heidegger also says this. Again, like when I woke up this morning, it's not like I have solved a metaphysical puzzle to get out of bed. No, my conscious brain did not even switch on. I got out of bed, and my id, to use the Freudian formula, was screaming at me that sort of I got to rush, or maybe it was my superego, that I got to rush to the university, otherwise bad things are going to happen to you because you'll be late, right? Not because I have sat down and rationally calculated, but because, again, so much of our behavior is actually, again, seems to be pre-programmed by these emotional patterns. So what I'm saying is that this is an unsolved problem. It may be an insoluble problem, but it doesn't really have all that much of an impact on everyday life, more or less. And again, if this was a proper philosophy of science course, this would be the beginning, the middle, and the end of it. Like 14 lectures about this. My personal subjective opinion is that this is interesting. For one lecture, maybe. 14 lectures, a bit too much. There was a particular year at ISAF when this was the standard syllabus, that not a single person chose philosophy of science course. After this, we decided that maybe we should switch the syllabus around. Anyway, well, again, you see, is this rational? Is this logical? No, it's irrational sociological reasons. We got to teach stuff that people find interesting, otherwise our department gets closed. So you see, the philosophical heavens and the bureaucratic earth. So my clock tells me that I ran out of time 15 seconds ago. Is that right? Yeah. Okay, colleagues, thank you so much. I hope this was fun. I hope this was interesting and elucidating. I find contemporary cosmology extremely stimulating in all sorts of ways. Thank you so much for your attention and your participation in the chat, which I will definitely read as soon as I get home. Otherwise, again, thank you so much for joining me today. And I will see you next Monday or next Wednesday. We'll see how it goes. And I think that's it.